Hey there, everyone. Again, this is Chem 120, General Chemistry. If you're joining me from Southern Maine Community College, hello, you're probably my students. So here we are, we're in Chapter 2 for the OpenStax Chemistry 2E class. And if you were with me for Chapter 1, you know the drill. So make sure that you have something to take notes on, maybe even like some printed slides. And you're going to need a couple of other things for this. Okay, if you're in my class, you should have a printed periodic table and you should have a printed ion list. Okay, so you need to pause the video if you don't have those yet and go get them. Those are really, really important. You're going to need them right there in front of you. For actual tests in the class, you're not going to be able to access another screen. And so you can't be looking for those in another place. I've had students try to cheat and use a periodic table on their phone, even in the tests on Brightspace, and that really, really doesn't work. You need to be able to see an actual physical version of the periodic table and your ion list, or you're going to spend a ton of time looking for stuff and it's not going to be there. And also it's against the rules. So, okay, the biggest thing in here, so we're going to start with a little bit about early atomic theory, the periodic table, and then we're going to get into what's really, really important in Chapter 2. And in Chapter 2, what's really, really important is nomenclature. So well, there's actually three things. There's number one, the ability to identify atoms, the ability to identify elements, to know what group they're in, and then to identify what kind of an ion they form, to understand mass, and then to put it all together as compounds and naming those compounds. Okay, so we're going to begin with Dalton's atomic theory, and Dalton's atomic theory is interesting for a couple of reasons. Okay, so first of all, Dalton's atomic theory had a variety of things in it, and a lot of it is still true. So let's look at number one. Matter is composed of exceedingly small particles called atoms. An atom is the smallest unit of an element and cannot participate, and that can participate in a chemical change. Yes, that is still true. Excellent. Good job, Dalton. The next one says an element consists of only one type of atom, which has a mass that is characteristic of the element and is the same for all atoms of that element. Oops, this is where Dalton got this one wrong. Okay, and later we're going to learn about something called isotopes. And that is going to help us understand why this is wrong for Dalton. The next one is that atoms of one element differ in properties from atoms of all other elements. All right, yay, Dalton, this one is still true. An atom that belongs to one element is completely different than another atom. So, for example, if you have an atom of silver or an atom of gold, you know that those are super different. If you have an atom of oxygen or an atom of hydrogen, also super different. There's nothing that overlaps between them. Okay, a compound consists of atoms of two or more elements combined in simple whole number ratios, okay? So in that compounds, the number of atoms of each of the element is always present in the same ratio, okay? So yes, this is still true. It's also called the law of definite proportions, which we'll get to. And last, it says that atoms are neither created nor destroyed during a chemical change, but instead rearranged to yield a different type of matter. And this is also true. You cannot split an atom. You cannot change an atom through a chemical change. And that's what the alchemists were desperately trying to do, to turn lead or other common metals into gold. And that is not possible. The only way to turn one atom into another atom is radioactively. So that would be a branch of chemistry called nuclear chemistry, where we're dealing with nuclear reactions. And you definitely won't be getting into that in Chem 1. Maybe Chem 2, but maybe not even until later. Okay, so now let's take a look at the law of conservation of mass, or the law of conservation of matter. It says if atoms are neither created nor destroyed during chemical change, then the total mass of matter present when matter changes from one type to another will remain constant. Great. Okay, so what does this entail? Okay, so what we have here is it means that if we have 4 grams of this and another 4 grams of this and 2 grams of this, then we're still, okay, that means that on our reactant side, our starting materials is another way of saying reactants. That means that on our reactant side, we have 10. units of whatever mass we're looking at. Okay, now here we are on this side. See, we have these here and here. So we still have 4 of those. And then here we have these little blue ones. Sorry about that. Let me go back to it. And then we have these little blue ones right here. And there's 2 of them, just like there were over here. And so those little blue ones are each a 2. And we would have 10 units of whatever we were looking at here as well. And that's really what this law is telling us. Okay, it's that what we start with, we have to also end with. Okay, so now we have the law of definite proportions, or also called the law of constant composition. And this is also part of Dalton's laws. It just wasn't called that at the time. Okay, and it says that all samples of a pure compound contain the same elements in the same proportion by mass. Okay, here we have a constant composition of something called isooctane. And isooctane is made of just carbon and hydrogen. Okay, now I haven't given you that formula, but what the law of definite proportions is saying is that the ratio is exactly the same. So in isooctane, if we have 14.82 grams of carbon and 2.78 grams of carbon, that ratio, 14.82 divided by 2.78, becomes 5.33 over 1. 22.33 divided by 4.19 becomes 5.33 over 1. We could do the same thing here. And my calculator is over there. So I'm going to set it up. And then while you guys are figuring it out, I'm going to run and go get that. All right. So here we have 19.40 grams of carbon, right, divided by 3.64 grams of hydrogen. I'm going to have to go back to the annotations tool because this isn't working very well. Okay, so you do 19.40 divided by 3.64. Here we go. Wait a minute. 19.64 divided by 3.64. Nope. 19.40. Got to put the right thing into your calculator. Divided by 3.64. Okay, and now adjusting for 3 significant figures, which is what I have here, then I get 5.33. Okay, and that goes grams of carbon on the top, and because we divided by the hydrogen, that gives us 1 gram of hydrogen. So we can see that that hasn't changed. Okay. So now let's take a look at the law of multiple proportions. The law of multiple proportions is really kind of tricky. Okay, so let's take a look at a couple of different possibilities here and see if I can kind of explain that. First of all, this is looking at 2 different substances. And in one of them, we have a ratio. All right, so the law of multiple proportions, it contains this ratio, okay? So they determine these ratios in the same way that we determined it on the last slide, okay? That law of definite proportions. So here we have 2 different compounds that contain chlorine, and that's Cl is a symbol for chlorine, and copper, Cu. Okay, and we put those together and we get a couple of different mass ratios. One, we get that in one compound, we have the ratio here of 0.558 grams of chlorine to 1 gram of copper. And in this one, we have 1.116 grams of chlorine to 1 gram of copper. And we get this 2 to 1, okay? And so this 2 goes with this one, and this 1 goes here. Okay, so that's sort of like saying, well, then you could almost say that maybe you have a ratio something like this, and then a ratio of something like this, okay? And you can do that for anything that you have. So let's take a look here. Let's say that we have water, H2O, and we have hydrogen peroxide, H2O2. Okay, so in this one, we have 2 hydrogens to 1 oxygen. right? And in this one, we have 2 hydrogens to 2 oxygens. And this is a way, the second way is a way of looking at it, not with masses, but with a number of atoms instead. Okay, now we have this interesting kind of mess in a way. Okay, and in the first one here, we have a compound in A. That's this green compound here. So here's a copper chlorine. And remember, this one was the 1-to-2 ratio. Okay. And then here in B, we have, I'm sorry, I said that backwards. This one looks like it might be the 1-to-1 ratio. And then this one would be the 1-to-2 ratio. Okay. And so you can see that multiple proportions will allow you to identify between those two. Okay, we're moving on through history. I'm not going, I want you to know Dalton's law and I don't want you to know the laws, but don't worry too much about each individual little experiment that was done. Scientist named Millikan did some studies with charged oil drops in order to determine the charge and the mass on an electron. Okay, and we'll get to electrons and protons and where they all are. But what he found was that there were these negatively charged particles inside atoms. And he found that the charge always had to do with this number, 1.6 times 10 to the negative 19th coulombs. That C is a coulomb. So this is really, really tiny. You don't need to know this for this class. I'm not going to have you calculating each one. We end up just end up saying it's -1 because the charge on an electron and the charge of the proton are perfectly balanced in the opposite direction. Okay, but then Thomson went on and we determined the mass of an electron, which is a little bit more important here. Okay, and the mass of an electron that he found here was 9.107 times 10 to the negative 31 kilograms. This is really, really tiny, right? Now, the SI unit, the System International Unit, for mass is the kilogram, but a lot of times we're going to end up doing our work in grams. And so just as a little review here, let's take a look at that. We have 9.107 times 10 to the negative 31 kilograms. And you remember from chapter 1 that when we convert, there are 1,000 grams in 1 kilogram. And so this will give you, so 9.107 times 10 to the negative 31st times 1,000 will give you 9.107 times 10 to the negative 28 grams. Okay. So it's going in that direction. All right, now we're moving on to a scientist named Rutherford. Rutherford was looking at the volume of an atom, and his experiments showed that an atom couldn't just have a whole bunch of stuff in it. It couldn't be like a stuffed animal with stuffing inside it. You know what I mean? Like if you have a stuffed animal and it's like a little stuffed ball or something, you've got stuff just all over inside it, right? Okay, so, but he said, no, that doesn't work. The atom must have this really big empty space in it. Okay, so what that means, what he found was that most of the atom, the mass, relatively heavy, you see it says here, the relatively heavy part is in this nucleus. Okay, so let's put all this stuff, here we have the nucleus, and we have all these particles stuffed together in a nucleus. Okay, and that is the atom's mass. Okay, the nucleus here has all of the atom's mass. Now, then we have these negatively charged electrons. Okay, and so let's come back here for just a minute. And right here, what we have is this nucleus is going to be positive. Okay, so then we have this negatively charged electrons, and the electrons are all around this. And so you could say, like I've drawn quite a few of them here. So let's draw an electron here, 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 an electron here. Okay, and there. That's a terrible rendition of an atom. But so here you have the nucleus here, and you have the electrons here. And I've on purpose not drawn it with those spiral orbits going around it because the electrons don't follow orbits. And when we start looking at quantum mechanics, we'll look at orbitals and we'll look at what that means. Okay. Okay. So where Dalton went wrong. Couple things here. Well, really just one. Okay. And the where Dalton got it wrong are the ideas of isotopes. And these are atoms of the same element that differ in mass. Okay. And so that's because they found neutrons. They were uncharged subatomic particles with a mass approximately the same as that of protons. Okay. So, and the neutrons are also in the nucleus with what we're working on. So let's take a look at what these isotopes might be. So most carbon is carbon-12. And carbon-12 has 6 protons, and it has 6 electrons, and it has 6 neutrons. Okay, and I just use this little neutron symbol here, N0, because it's uncharged, it's neutral. Okay, so you have in carbon-12, you will have 6 positively charged protons and 6 neutrons and 6 electrons. And the protons and the neutrons are in the nucleus, and the electrons are sort of all over outside of it. Now, you probably haven't heard of something called carbon-13. Okay, carbon-13 makes up about like 0.1% or 1.1% of all carbon. And carbon-13 has 6 protons in it, 6 electrons if it's neutral, and it has 7 neutrons. So that makes it a little bit heavier. Now, what you guys have probably often heard of is something called carbon-14. I don't know why it's making these streaks on it. Sorry. Okay. Is carbon-14. Now, carbon-14 is very minuscule. It's less than 0.1%. It just makes up a very, very small amount of carbon, but it's the carbon that's radioactive. And it's the carbon that's used in carbon dating that we use to radioactively date certain materials. Now, carbon-14 has 6 protons in the nucleus and 8 neutrons in the nucleus and 6 electrons outside the nucleus. And Dalton didn't have any way of determining that there were these different things within the carbon, but later, like Chadwick did. Okay, and so that's where this comes from. That's where these isotopes come from. This is also why when you look at the periodic table, it doesn't say 12 for carbon, it says 12.011. And we'll get to that a little bit later, but that's because it's a weighted average of all of these different isotopes. Okay, so now let's think about atomic structure and its symbolism. The nucleus contains the majority of the atom's mass. And by the majority, you could say that the nucleus is about 2,000 times heavier than the electron cloud. Okay, and it's all in the center. So let's say that this dot right here, let's not pick that dot. We'll pick a dot right here in the center. There you go. There's our nucleus, that tiny little dot. If you're looking at this on a phone, you probably can't see it. Okay, all of our mass is right there. And now here is the rest of our atom, not drawn to scale. Now, if I had a bigger screen and I could make this circle like 20 times bigger, that would be the size of the atom as a whole. And all of that space is empty, no mass for the most part. Okay, but here we have the nucleus, and it contains pretty much all of the atom's mass. Protons and neutrons are much heavier than electrons by over 1,000 times, so way more. The electrons, however, occupy almost all of an atom's volume. So all of the mass is in the center, and those are the protons and the neutrons, and then around that is our electron cloud. So the electrons, no mass, all of the volume, and so it's reversed like that. The diameter of the atom itself is 1 × 10⁻⁻⁻ meters. So only one significant figure there. So we know that that's kind of, that's just a guess, right? It's not going to be very good. So that's a good way of saying, you know, we're just saying that the diameter of any atom is about 1 × 10⁻⁻10th meters. But because we only have one significant figure there, we know that that's not going to be real accurate. Okay. Now, a lot of times diameter isn't what we're looking for. So let's think about what a radius is. Okay. A radius, remember, is half of the diameter. So if we have 1 × 10⁻10th meters, whoops, sorry, for the diameter, then the radius is going to be 0.5 × 10⁻10th meters, or better, 5 × 10⁻11th meters. Okay. The diameter of the nucleus is 100 times smaller, okay, at about 1 × 100,000 times smaller, at about 1 × 10⁻15th meters. So again, that means that the radius of our nucleus, and I'm actually going to turn this into an approximate symbol because that's not exact. The radius is then going to be 0.5 × 10⁻15th meters, or better, 5 × 10⁻16th meters. Okay. Okay, so this just gives you a little bit of an example of what we're actually looking at here. If the nucleus is the size of 1 blueberry, there we go, 1 blueberry, and you were to take that 1 blueberry and put it right there in the middle of your football field, then the entire football stadium would be the empty vacuum except for the electron cloud. And when you start really wrapping your head around that, that is crazy. And it is so small that you can't see the atom. You can't see the atom with a microscope. So it's a very, very interesting thing. All right, now let's think a little bit about units. Okay, atoms and subatomic particles are really, 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 really small. Okay, a carbon atom has a mass of less than 2 × 10⁻23 grams. So you can see that it really does not make any sense to talk about the mass of a single atom in grams because we don't have any way to conceive of that. Okay, so instead what we've done is we've said, okay, let's define something called the atomic mass unit, or the AMU. A carbon-12 atom, remember, has 6 protons and 6 neutrons. And there's carbon everywhere. There's carbon lying around. It's really easy to get. And so we're going to go ahead and base the atomic mass unit off of carbon. That's what the scientists said. And they said, just to make things easy here, let's just define the atomic mass unit as 12 atomic mass units for 1 carbon-12 atom. What that means is that an atomic mass unit is equal to 1.6605 × 10⁻24 grams. But it gives us a way to talk about the mass of a single atom without not making any sense at all. Okay, so let's see. Well, where am I at in my slides? I get to talking and I forget where I am. Okay. So here we are in our properties of subatomic particles. Okay, so first of all, we have our protons inside our nucleus, and a proton is 1.0073 atomic mass units. Okay, so hang on just a second. Let's go page up for a minute and let's write some of this down. Oh, actually, I have it right here. Okay, so let's come back to this and let's put these in terms of something that makes sense. So here we've said that, and we're going to call the charge on a proton +1. So let's take this atomic mass units and let's find out what the mass of our proton is in grams. Okay, so remember that 1 atomic mass unit is equal to 1.6605 × 10⁻24 grams. Okay, so let's figure out what's the mass of a proton. Okay, so we have 1.0073 times 1.6605 EE, remember that EE button, 24 negative, it needs to be a negative 24. All right, now if you're doing that on your calculator with me, which I really highly recommend because it'll mean that you'll get the same answer that I will on a test, which is, you know, the important part here. We can have 5 significant figures with these. Okay, so we get 1.6726 times 10 to the negative 24th grams. Okay, and that is the mass of 1 proton. Okay, now next we have the neutron, and it's also inside the nucleus, and it has no charge. Okay, it doesn't contribute electrically, and it's a little bit heavier than a proton, 1.0087 atomic mass units. So let's try that, 1.0087 atomic mass units. And again, we can use that conversion factor to find this, and we have 1.6605 times 10 to the negative 24th grams. Okay. 1.0087 times 1.6605 to the negative 24th. Okay, and with my 5 significant figures, what I get here is 1.6749 times 10 to the negative 24 grams. Okay. And now lastly, we have our electron. And remember that electron is an electron cloud outside the nucleus, and it's very small, 0.00055 atomic mass units. Oh, phooey, it only gave us 2 significant figures here. All right, so let's go ahead and convert that as well. And I'm setting this up exactly like we did before. Times 1.6605. And now I get 9.13. I'm going to go ahead and go with all of those. And you can see that this is matching what we had found before, times 10 to the negative 28th grams. Okay. And now you can see how we're much, much bigger. We're almost 2,000 times bigger for the mass of a neutron than an electron. That gives you some idea of where those are. The thing to really remember here is the mass, the charge on a proton is a +1, which is why I will often abbreviate a proton as a P+. The charge on a neutron is 0, which is why I will often abbreviate that as N0. And the charge on an electron is -1, which is why I will often abbreviate that one E-. Okay. Okay, now let's take a look at a couple of other things. Here we start with an atomic number Z. Okay, now we're going to take a look at a few of these. But first of all, the number of protons in the nucleus of an atom is its atomic number Z. So that's the one thing that never changes. Carbon always has 6 protons. Okay, so the number of protons is the thing that never, ever, ever, ever changes about an element. Okay, if we are making an ion, we can remove or add electrons. So sometimes the number of electrons that we have will change to make ions. If we're talking about isotopes, we know that sometimes we have different numbers of neutrons contributing to different masses. But the number of protons is the thing that never changes. So our atomic number is called Z. And in case you're wondering, I would have to look that up. I don't know off the top of my head why it's called Z. Okay, these protons are a defining trait of an element, okay? So no matter where you go, that's what you're going to see. And how far do I have to go to find a period? Oh my goodness, let's flip out of this just for a moment. And let's go, I need to actually, let's see, I have to stop the share. And then let's go over here to a periodic table. Okay, that's kind of, there we go. Okay, so let me see here. There we go. Okay, hopefully you can see this and I haven't totally messed it up and shown you the ion list. I won't be able to, I can't see that from here. Okay, so, but what I do here is I have here, mine is printed in black and white right here, but we have a periodic table. Actually, I'm going to make sure that I really do share screen. There we go. Okay, just in case. I didn't want to have that be the wrong thing up. Okay, so here we have a periodic table. Okay, and this this one is from Web Elements, and I really like this one. I think it's really clear. One of the problems with this one is that it doesn't show you groups. Okay, and groups are going to be very important, but it's very clear. It's very easy to read. This is the one that I really want you to print. You can print the full color one too if you want to, but this is the one that needs to be printed. And here, when we look at this, you can see on the key right here that here you can see where it says atomic number right here. Okay, that's what refers to this 5, 6, 7, 8. 31, 32. Okay, so what you would do is you would say, okay, xenon here has an atomic number of 54. Okay, argon has an atomic number of 18. Boron has an atomic number of 5. And so remember, this atomic number is our number of protons. It's the number of positive charges that we have in there. Now, what I'm actually going to do, I'm looking here, and I'll come back to this. Okay, all right. My only way to do that is to clear my drawings. Annotate, stop share. Sorry, this is so complicated. Okay, so here we are on our atomic number Z. And one of the things, okay, actually let's, I'll go ahead and draw this. Okay, so here we go. Let's draw, as I'm looking here, we'll draw something crazy. We'll draw actually, let me annotate it for a second. Okay, so here I'm going to draw osmium. Oh, this is crazy. I've never used osmium a day in my life. Okay, osmium, O-S-M-I-U-M, osmium. And osmium is number 76. And then we have this OS right here, okay? And then it says 190.23, okay? And what this means here is that osmium has 76 protons. All right, so page up. You can't really see that. Okay. Okay, so now what we're doing is we're saying, well, nature is neutral. Now, we start out talking about neutral atoms, okay, not in compounds. And a neutral atom must contain the same number of positive and negative charges. And so that means the same number of protons and electrons, okay? They have to be equal. All right, so that means that neutral potassium has 19 protons and 19 electrons. Okay, and potassium is right here, potassium. And if you're looking for it, we have a 19 here, and it says K. The symbol for potassium is K, and the mass of that is 39.098. And then here it shows us oxygen. Okay, so symbol oxygen is 8, is O, there's an 8 above it, oxygen. Okay, and underneath it, it will say 15.999. Okay. All right, now the next thing that we have here is our mass number. And our mass number is the number of protons plus the number of neutrons. So A, mass number, is equal to protons plus neutrons. Okay, and so where does that go? So A minus E equals the number of neutrons. Okay, so we had some things in here. Remember on the previous one, okay, so we've talked a little bit about isotopes. So let's take a look at what these would be. Okay, so, and this is going to be kind of a direct reference to your recitation. Okay, so now if we look at, let's look at carbon 14. Okay, and that was an isotope that we said was radioactive, used in carbon 14 dating in a previous slide. And if we look at carbon 14, okay, we know that because on our periodic table here, okay, so it says carbon, and then there's a 6, and then there's a C, and then it says 12.011. Now, the fact that this is 12, okay, so this 6 is our atomic number Z, and it's our number of protons. This number here is our mass. And this here in the periodic table is the average mass of all isotopes. Now, at the beginning of your recitation for chapter 2, and in a previous slide, we talked about some different ones. And so this is the average mass of all isotopes. We have carbon 14 and we have carbon 13, right? And we have carbon 12. Okay, so carbon 14, we had said in a previous slide, had 6 protons and 6 electrons and 6 and 8 neutrons. So notice how this 14 is equal to 6 plus 8. Okay, now we have this carbon 13. Well, carbon always has 6 protons, and in its elemental state, not an ion, it also has 6 electrons. So 13 is equal to 6 plus 7. So that means that our number of neutrons is 7 neutrons. And then we have this carbon 12 here, okay, running out of room, but we know that it's got 6 protons and that it has 6 electrons. And we've got this 6 here, so it's 6 plus 6, which means that carbon 12 has 6 neutrons. So you can tell from this, if this is the average mass of all the isotopes, then we must have like 99% has to be carbon 12 in order to have a mass number right close to 12. Okay, so how do we put these in place? Let me draw a few more things here. Okay, so here we had carbon 14. So whenever we draw a symbol, here's our symbol X, and that's our element. And then on the top, you're going to have your mass number A. Okay, and then on the bottom, you're going to have your atomic number Z, and that's going to identify this. So these neutral compounds of carbon 14 would be 14, C, and 6. And carbon 13 would be 13, C, and 6. And carbon 12 would be 12, C, and 6. Okay. Okay, now sometimes in the previous example with carbon, we saw that all of our stuff was equal, okay? So our protons and electrons were exactly the same. Well, sometimes an ion is something that has either lost or gained electrons. The number of protons still never changes, okay? So we make ions by losing or gaining what were electrons. Sorry, protons don't change. We lose or gain electrons. We're not going to lose neutrons either, unless we're dealing with nuclear chemistry, which again, not doing in Chem 1. Okay, so let's think about some different kinds of ions. So we have 2 different kinds of ions. We have cations and we have anions. And cations are positively charged and anions are negatively charged. Okay, so an atom that gains 1 or more electrons will have a negative charge, and it's called an anion. Okay, so oxygen becomes oxide by gaining 2 electrons. Okay, so I'll show you that in just a minute. And then on the other side of that, an atom that loses 1 or more electrons will exhibit a positive charge and is called a cation. And neutral sodium will do this. It'll lose an electron to become a sodium ion. Okay, so let's take a look at what that would be. So neutral oxygen will look like this. Oxygen. Okay, let's say that we're dealing specifically with we'll just say so oxygen has 8, and we're looking at our most common isotope for oxygen, which is 16. Okay, and this neutral oxygen has 8 protons and 8 neutrons and 8 electrons. All right, now if oxygen gains 2 electrons, now we have the oxide, or the we'll call this oxide. Okay, and this is on your sheet. And so we have oxygen, we still have a 16 here and an 8 here, but we show those extra 2 electrons with a 2- charge right here. So notice there's nothing up here in this upper right-hand corner on the neutral oxygen, but on the oxide anion, we have this -2 here. Okay, and this one will have 8 protons and 8 neutrons and 10 electrons. Okay. Now let's look down here at our sodium. All right, now sodium, we can look at our periodic table. Okay, and sodium is number 11. Okay, it tells us here Z is equal to 11. So neutral sodium, and sodium is Na, kind of it's one of those that doesn't really match. So neutral sodium with 11 and a mass number, the most common mass number is 23. And this one is neutral. And that means that it will have 11 protons and 11 electrons. Now remember, atomic number plus neutrons equals our mass number, which means that this one will have 12 neutrons. Now, what happens is sodium can lose 1 electron to become sodium ion. Okay, and here's the interesting thing here is that the cations, the sodium cation, the name doesn't change. So oxygen becomes oxide and sodium just stays sodium cation. You just have to say that it's the cation. And now in this case, we have our sodium here and we still have the same mass number and the same number of protons because electrons don't change that, but we've lost 1 electron. So here we have 1+. Okay. Sometimes it's written as 1+, but sometimes it's just written with a single plus sign like that. Okay, and in this case, we have 11 protons and we have those 12 neutrons still. That hasn't changed, but we've lost an electron, so now we have 10 electrons. All right, now let's take a look at some chemical symbols. So you've already seen this a little bit. Chemical symbol is an abbreviation that we use to indicate an element or an atom in the element. Some symbols are derived from the common name and some abbreviations are from another language. Usually that language is going to be Latin or Greek. So sometimes they won't match. So oxygen is an O for oxygen, but mercury is Hg. So be on really close lookout on your periodic table, not just for the symbols, but the names. And some of them are really close and you think, ooh, you know, what could that be? So, so watch those really, really carefully. Most symbols have 1 or 2 letters. Some of the smaller ones have 1, but 3-letter symbols have been used to describe some of the elements that have atomic numbers greater than 112. We aren't going to be dealing really with those really, really massive numbers, those massive elements, mainly because they're not something that exists in nature. There's something that's been made in a laboratory and they're not used. They're not useful in the term of actual chemistry. Outside of like nuclear chemistry, they're not useful because they don't exist in nature. Only the first letter of a chemical symbol is capitalized. Now, this is really, really, really important. And let me explain why that's really important. Okay, so chlorine is Cl. Okay, and we know that this is only one. Let me see if I can come up with one of the examples for why that ends up being really, okay, so sometimes people will see this Cl together is chlorine. You can look on there. Now, if I wanted like a carbon and an iodine together, I would make that I really capital. So for example, iodine is I. So let's take a look at something. I won't worry about that. Just make sure that your second one is always chlorine. Okay, so magnesium, Mg. Okay, that's magnesium. This is one of those places where if you spell it incorrectly, you will be wrong. And the reason for that is not because I care how you spell things. It's because in the chemical world and in the medical world, a slight change in spelling will change your compound enough that it might be something simple as it doesn't work anymore, but it might be something damaging as in it kills someone. Okay, so the ability to spell and have capital versus lowercase correctly all the time is critical because either your product or someone's life could depend on you being very careful with those things. So this is one place where you have to be very, very careful to make sure that your spelling is always correct, that your capital letters versus lowercase letters are always correct. Okay, so this slide is just a little bit of an example of where some of these come from. And the only reason this is in here is because first of all, you're going to usually be getting it from your fancy periodic table that hopefully you have printed just like me. But I liked this slide mainly because it shows you where things come from. Okay, so mercury comes from yeah, okay, so mercury, it's easier to say. But ferrum, plumbum, calcium, so those kind of those Latin names as well. You don't have to know them. I'm not going to ask you what the Latin name is for iron, but you will need to know that iron is Fe. Okay, so let's take a look at isotopes. We've looked at this a little bit before. I like to do that in the slides, is introduce things in multiple places. Isotopes, the symbol for a specific isotope of any element is written by placing the mass number as a subscript to the left of the element symbol. Okay, so the atomic number is sometimes written as a subscript to the left. Okay, that's, oops, sorry. Okay, so for example, magnesium can be magnesium 24, magnesium 25, and magnesium 26. You'll see this like this, but sometimes it's not so easy to make a superscript ahead of time. So the other way to write these would be like this: magnesium 24. Okay, like if you are working on something and your computer won't do this, magnesium 24 or Mg 24. Okay, I've also seen it written like this as well, and magnesium 25 or Mg 25. Okay, so instead of like this, you can do this, and this shows your mass number. Okay, remember that's A. All right, all isotopes of magnesium have 12 protons, but the number of neutrons is different. So for magnesium 24, we have 12 protons and 12 neutrons. For magnesium 25, we have 12 protons and 13 neutrons. And for magnesium 26, we have 12 protons and 14 neutrons. Okay, so let's see, do you remember this symbol? Okay, so this symbol, we had X, and we had our mass number A on top and our atomic number Z on the bottom. And up here, I'll put a box. This was our charge, okay? If it's neutral, it has nothing. So if you look at these, this shows the ions for helium with a 2+, and the ion for magnesium 2+, Okay, if these were neutral, it would look like this: He 4 and 2 and Mg 24 and 12. Okay, and that's what they would look like if they were neutral as opposed to ions. All right, now let's just, as kind of a little bit of a review here, this one, helium here will have 2 protons, and that 4 means that we have 2 neutrons, and we have no charge, so 2 electrons. Up here, we've got this 2 plus charge, so this will be 2 protons, right? And the 4 means that we have 2 neutrons. Now take a look at this. We have 0 electrons. If you've ever heard of an alpha particle, a helium nucleus right here is an alpha particle. Now let's take a look at our magnesium over here. When we're neutral, we have 12 protons and 12 neutrons, and our protons and electrons have to be balanced, so 12 electrons. And I got that 12 neutrons because of our mass number here. But on up here, when we have our magnesium, again, that would be 12 protons, mass number 24, so we still have 12 neutrons, but we have a 2 plus charge here, which means that we have 10 electrons. Okay. Here are the isotopes of hydrogen, where we have protium, which is usually just called hydrogen, okay? Nobody walks around calling hydrogen protium unless you're trying to differentiate it. Usually when you say hydrogen, you mean this. But then you also have a little bit of deuterium in there and a little bit of tritium in there. And this trace means that it's not real close. All right, so let's use this to take a look, and it's the next slide as well, but let's use this here to take a look at what this means. Okay, so here we have 1.0078 and deuterium at 2.0141. There's so little tritium out there that it doesn't fit into our weighted average. So the mass on the periodic table is 1.08. Well, no, 008. Okay, and that's what's on your periodic table, 1.008. I've also seen it as 1.0079 if you have a periodic table that has 5 significant figures on it, okay? All right, so this is with 4 sig figs, and this is with 5 sig figs. So let's take a look at where you can see that this one comes very close, and this is one that's really far off. So why isn't it more balanced? Okay, the reason is because the mass numbers on the periodic table are what we call weighted averages. Okay, and you're gonna, again, this is sort of a preview of the next slide. Okay, so the mass number on the periodic table is a weighted average. And basically what that is saying is that in some cases we have a longer, we have a more of an importance from one thing versus another thing. Okay, so let's take a look at that. All right, so the way we would find this weighted average from here is that we would see, okay, so you have this 99.989, and so you make it 0.9989 times 1.0078 plus, and now we look at this one, we have 0.0115%. This becomes, when we turn this, so we went from a percent to a decimal, this will become 0.000115. 0.000115 times 2.0141. And if you have a calculator, go ahead and pull it out and do the same thing. 0.9989 times 1.0078 equals, okay, plus, and now I need to have my parentheses in there, 0.000115 times 2.0141. Okay, something came out not right. Hang on. Okay, this example isn't working. So what that means to me is that there must be an error somewhere on the slide. Oh no, I see it. I see what I did. Okay, see, look at this. So this is just proof that we can all make mistakes. See this? It's 99989. Okay, so it's always kind of good. Double check yourself, because I can make mistakes when I'm doing math by not looking carefully enough, even though I'm really good at math. So everybody, make sure you're checking real quick. Now let me try this again. 0.99989 times 1.0078. Ah, now I have a different number. Plus 0.000115 times 2.0141. There we go. Now what I get here is 1.007920764. Okay, I can actually only have 3 significant figures. See this? This one only has 3 significant figures. Okay, so then you would have 1.01, but you can see then where this matches. All right, so what this slide is doing is this slide is just showing you exactly what we did before, but it's showing you that weighted average for boron. Okay, so go ahead and look over this and just be aware that it's in here, this weighted average. Okay, let me look. I think that's a good place to stop for this first video. Okay, and we will come back in a minute and talk about chemical formulas. All right, take a bit of a breath, get a snack or a drink of water, and we'll come back in just a bit.